All right, today we were going to continue talking about the stability of trajectories and particularly periodic orbits. You could use the method I talked about last time to get the stability of any trajectory, even over the short term. It takes small displacements. If you remember the picture we had, you've got some kind of reference trajectory that I'll call x bar of t, and maybe you're trying to get the what some nearby trajectory does, how it evolves. So we look at, we assume that this other trajectory that we'll call just x of t is displaced only by a small amount. So here is the initial displacement, and then at some later time, the red trajectory is displaced a different amount, and the initial displacement is related to this displacement after an elapsed time t through this state transition matrix. And this only holds in the, it's kind of a linearization of the dynamics around the reference trajectory. So this is only as good as the linearization, meaning if you ask me how close do I have to be to the reference trajectory, I don't know. But this holds in the limit as x, the red trajectory, is extremely close to x bar. But I mean, this gets used in numerical situations quite a bit. So we're now going to specialize to the case of a periodic trajectory. And maybe I'll write up here what our ODEs are. X dot is f of x, and we're looking at x is an Rn. So this is an n-dimensional autonomous ODE. We haven't yet specialized to the case of ODEs that come from mechanics. Coming from mechanics will lead to something, but we'll talk about that later. And maybe even get to chaos, because chaos in Hamiltonian systems is often related to unstable periodic orbits. All right, getting ahead of myself. So let's specialize to the case of x bar is a periodic orbit with period capital T. So the picture that we should have in mind is x bar. Now it's not just going anywhere, it actually goes back onto itself. And maybe there's some, I'm just kind of highlighting some initial condition on the periodic orbit. So periodic means that if we're here at this point, and then we wait an elapsed time, capital T, we'll be back at the same point, no matter where we are. And why did I highlight one specific initial condition? It's because we imagine we could put down a Poincaré section. So here's sort of a small Poincaré surface of section that's perpendicular or transverse to our periodic orbit. And we want to know what happens to nearby trajectories. So here's a nearby point on that Poincaré section, and maybe this will do some interesting things going in and around our periodic orbit. We don't know. Where is it going to end up? So we look at the initial displacement vector in the Poincaré section. So y0 is the initial displacement away from the periodic orbit. in some sense, where this Poincaré section is pretty arbitrary. I could pick any place along the periodic orbit. The main thing is the Poincaré section can't be along the periodic orbit. It has to be perpendicular to it. So it needs to, it doesn't even have to be perpendicular. It just has to be transverse. You just don't want to be along it. You want it to be transverse, meaning it intersects. The Poincaré section intersects the periodic orbit. Or transverse to X bar. Okay. So now, now what? What did we talk about last time? We talked about the linearized dynamics along the periodic orbit. Actually, last time we talked about linearized dynamics along the trajectory, but now it's along the periodic orbit. It's given by the Jacobian of our ODEs up here, the right-hand side, the Jacobian of F evaluated along the periodic orbit. And this is going to be, like we talked about, a time-dependent n by n matrix. And now it has the property that it's not just time-dependent, it's time periodic. So if we were to wait a time capital T, this matrix repeats. It's a matrix of periodic coefficients. So this is just the same as the Jacobian evaluated along that periodic orbit. Because it's a periodic orbit, the linearization is also periodic orbit, and that's all summed up in this A matrix. So, so now we're, when we solve for the phi matrix, the state transition matrix, it's given a special name, but we'll get to that. So we can solve for the phi matrix. In particular, the time that we most care about is one period. So what happens to nearby initial conditions near this periodic orbit after we come around once? It's like we start on that Poincaré section and then we come back again. So we want to solve phi of capital T. And if you remember from last time, how do we do this? We'll have n plus n squared ODEs to solve. So we solve the original equations of motion. We assume through some process, we've identified an initial condition that's on the periodic orbit, this X bar 0. And then the n squared ODEs we're solving are the ODEs for this n by n state transition matrix, which will be A times phi, with the initial condition that phi at time 0 is the n by n identity. Okay. So we solve those n plus n squared ODEs. And you know, integrate. Usually this is done numerically. You don't do this analytically. So you integrate from time t equals 0 to t equals capital T. And t equals 0 is just the time of the initial point on there. We call phi of capital T, so the linearization of the dynamics around the periodic orbit after one period, it's exactly the same in concept as the M matrix that we had talked about before when we first studied that simple kind of vibrating the pivot up and down by changing gravity. We called that M, and maybe we didn't give it a name back then, but for historical reasons that escape me, it is called the monodromy matrix. And that's where the M comes from. And so what does that mean? All right, so over here, this initial picture of, here's this vector, initial vector. Well, if we start with an initial point that's near the periodic orbit that's close enough, then it'll end up going to here, which is y after capital T, and that's just going to be m times the initial displacement vector. So things map according to this matrix equation. So y of t is m y of 0. In some sense, this is a linear approximation of the Poincaré map transversal to the periodic orbit. Right? In general, Poincaré maps aren't linear, right? They're just kind of following trajectories around. They're very nonlinear. This is a linear approximation to the Poincaré map, right? That's the map that takes points on this Poincaré section and maps them. You know, how do they return to this Poincaré section? Linear approximation to the Poincaré map that's, you know, transversal to the periodic orbit x bar. Okay. And so y0 equals 0. If you have 0 displacement, that means the periodic orbit. This is the periodic orbit itself. And if we want to know what the dynamics are like near the periodic orbit, or in other words, if we want to know the stability of the periodic orbit, all we have to look at in this linearized limit is dynamics due to this linearization equation, which will then boil down to finding out what are the eigenvalues of M, eigenvalues and eigenvectors. So this is, it's similar to some things we've done before. And I think near the beginning of the course, we talked about looking at equilibrium points of a continuous system. So equilibrium points of the ODEs and what's the stability of the equilibrium point. We're not talking about an equilibrium point now. Now we're talking about a fixed point. This is a fixed point. This initial condition on the periodic orbit, think of it as a fixed point of the Poincaré map. And we want to know what are the linearized dynamics under the map in the vicinity of this fixed point. So it's the eigenvalues and the eigenvectors. Whoops, must have pressed the button wrong. I'm going too fast, that's why it happened. It's the eigenvalues and eigenvectors of M, the end by end matrix M that we have numerically computed typically, except in some special cases where we can get it analytically, like we looked at a few weeks ago. Eigenvalues and eigenvectors of M reveal the stability of the periodic orbit. Why is that? It's because the eigenvectors and eigenvalues of M reveal how the nearby perturbations either grow or shrink or rotate or whatever they do. So we could think of this as revealing the stability of the periodic orbit. Also, more generally, we could think of it as revealing what the phase space is like near the periodic orbit. And these are, in some sense, equivalent. Stability of the periodic orbit is related to revealing the phase space near the periodic orbit. Sometimes we just ask yes or no questions like, is it stable or not? maybe that's all you care about. But you could actually, you get more information from the M matrix than just, is it stable or not? All right, so let me tell you some things about what the eigenvalues of M will be.
This is all Floquet theory, right?
Yeah.
Okay.
Well, Floquet kind of makes it complicated.
Oh, I see.
Especially in the original French.
Oh.
But yeah. He did something more general about the solving ODEs that were of the form like x dot equals a of t x for periodic A, which is basically what we're doing here, but we're kind of couching it in this Poincaré section language. He did something more general in like the late 1800s, I think. I can even post his original paper, which is in French. And he did it, I think around the time of Mathau's equation. So all of that, was kind of heating up in the 1800s. Anyway, so the eigenvalues of M, I'll call them, because I'm not very creative, lambda 1 through lambda n. And they are called the Floquet multipliers. And I prefer names that don't have someone's proper name attached to them. So I sometimes call it the characteristic multiplier. And that you might see things like that in books too. So it's either called a Floquet multiplier or a characteristic multiplier. Why is it called a multiplier? It's called a multiplier because the corresponding eigen value, let's call that E1. And let's say that this is the direction E1. If I had a displacement in that direction, exactly in that direction, and let's say lambda 1 is something much greater than 1, then after I've gone around the periodic orbit once, I will map in that same direction. Y of t is going to be lambda 1, y0. So I've just sort of multiplied in that direction, multiplied my displacement. Now I picked something where lambda was greater than 1. If lambda was less than 1, that means that a perturbation in that direction will actually shrink. Now there's no requirement that these be real. But let me just give another name that people will use here. They'll sometimes write for each eigenvalue, usually if it's real, they'll write it as e to the sigma I t. And this defines a number, sigma I. It's called the Floquet exponent. Or we could call it the characteristic exponent. And it's related to another concept you might have seen. Sigma I is also called a Lyapunov exponent. Sometimes, so this means our system could have n Lyapunov exponents. Sometimes people talk about just one Lyapunov exponent. They usually mean the maximum Lyapunov exponent, because over the short term, the direction where things grow the most is going to dominate. Well, I shouldn't say short term, over the long term. If there's any direction where the growth is the most, any generic initial condition is going to be, after a while, aligned with that direction. So you may have heard of Lyapunov exponents. Now, where the analysis of the eigenvalues differs from what we might be used to from looking at a continuous system. For a continuous system, you look at our eigenvalues in the right half plane or the left half plane. Because this is a discrete system, we're looking at a map. Right half plane, left half plane doesn't matter. It's the unit circle that plays the key role now. So let me just write that. The unit circle in the complex eigenvalue plane plays an important role dividing stable and unstable behavior. So what does that mean? Let me plot, if you haven't seen the unit circle. Sure, there's some function that'll just plot me a nice pretty circle, but this is good enough. Okay, so unit circle, we're talking about it's one distance of unit 1 away from the origin. So it intersects 1, -1. It also intersects I and -I. And it's the whether the eigenvalues are inside or outside the unit circle that plays an important role now. So let me, here's like a typical eigenspectrum. There'll be some things that are real, and then there'll be complex conjugate pairs. So M, because it's an n by n matrix, and it's real, it has n eigenvalues, right? And we describe them, lambda 1 through lambda n. And +1 is always an eigenvalue. You might wonder, okay, all right, why? It's always an eigenvalue with the eigenvector pointing along the periodic orbit. So if I've got my periodic orbit, here's my point x0 bar along the periodic orbit. There's going to be that direction, the direction that's tangent to the periodic orbit is the same as like the instantaneous change, but it's also equal to f evaluated at that point. And why is the eigenvalue 1? What this means is that if you perturb in the direction of the periodic orbit, then that perturbation will not grow or shrink because it's still along the periodic orbit. Remember, we're looking at infinitesimally small. So if you do infinitesimally small perturbation along that direction, it's just another point. You're on another point on the periodic orbit. So think of two train cars following each other around. Because they're on the same train, they're not going to get further or closer. So +1 is always going to be an eigenvalue with an eigenvector pointing along the periodic orbit. So something that is along F, remember that's our right-hand side, the vector field, F evaluated at the initial condition point. All right, so that means we still have n-1 eigenvalues, and stability is determined by those. And if I were to plot my Poincaré section. The Poincaré section is always one dimension less than the ambient space. So this is an n-1 dimensional subspace. So really these other n-1 eigenvalues, their corresponding eigenvectors span this space. They span this tangent plane, which has, right, here's the vector that's pointing along the periodic orbit. Okay. So what about these other eigenvalues? Well, eigenvalues that are, I guess I could plot it here with this unit circle stuff. If you're inside the unit circle, that corresponds to stability. These being multipliers, these will correspond to directions in which the perturbation, the magnitude will actually shrink each time because we're in the unit circle. If outside the unit circle, even if it's on the left half plane or right half plane, doesn't matter. If an eigenvalue is out here, that means that those are directions where things will grow. And if you're exactly on the unit circle, that corresponds to directions where perturbations will keep the same magnitude. They might rotate, but they'll keep the same magnitude. So we could say these correspond to unstable directions, inside corresponds to stable. All right. And I can summarize that in terms of eigenvalues with we're talking about the modulus, because these could be complex numbers. If the modulus is less than 1, that means inside the unit circle. And that corresponds to stability. In fact, the concept is called asymptotic stability, meaning you will asymptotically, if you have a perturbation along that direction, it will asymptotically approach the fixed point. If you have eigenvalues that are exactly on the unit circle, spell an eigen all weird. So if the modulus equals 1, so that's on the unit circle, we could call those neutrally, the corresponding eigenvectors are neutrally stable directions. There's no asymptotic stability. The perturbation doesn't shrink, it just doesn't change in magnitude. And of course, that's the dividing line between stability and instability. So eigenvalues with their modulus greater than 1, that's outside the unit circle. This corresponds to instability. Or those are unstable directions. So let's just go through some conceptual examples to give you the idea. Let's just suppose we're looking at a 3D world. So x dot is f of x, where x is R3. So 3D, not 3 degrees of freedom, it's 3D. Then our Poincaré section is 2D. And here's our periodic initial condition along that periodic orbit with its the direction that's tangent to the periodic orbit. Here's our fun little periodic orbit sketched out. Whoa. Let me just give a couple of possible scenarios. We know that one eigenvector is always going to be equal to 1. So if I plot the unit circle, this is the plane where I'm plotting my eigenvalues. There's always going to be an eigenvalue 1. And let's suppose that I've got a complex eigenvalue that's inside the unit circle. Well, if I have 1, then because this is a real matrix, I have to have its complex conjugate. So that means I've got 2 things inside the unit circle. So what the dynamics look like along the Poincaré section, we can sketch that out. So here's the sketch of what things will look like on the Poincaré section. We've got the fixed point, which is the periodic orbit, initial condition along the periodic orbit. And if I have some initial point here, we could think of that as an initial perturbation vector, y0. And the dynamics are given by these two, the eigenvectors corresponding to these 2 eigenvalues that are inside the unit circle. So the magnitude of that perturbation vector, the orange thing, has to shrink. It might get rotated, but it'll shrink. So here's y after a time t. Now I'm here. Now y after some other time. I'll just plot the tip of it, the red point, and it's like I'm spiraling in. This thing will asymptotically approach the periodic orbit. So this would be like the 0th piercing of the Poincaré section. Here's the first one, and here's the second one, third one, fourth one. You know, as n goes to infinity, I'm having y n t goes to 0, shrinking. Y going to 0 means the perturbation away from the periodic orbit is going to 0, which means the periodic orbit is asymptotically stable. So for this case, the periodic orbit is asymptotically stable. That doesn't mean it's globally stable. That's another concept. What we are determining is local stability, meaning locally in phase space. There might be some other periodic orbit that is also asymptotically stable. In fact, those periodic orbits we were looking at as part of the Duffing system, where we had the tilted resonance curve, that had 2 asymptotically stable periodic orbits that were separated by an unstable periodic orbit. So those 2 were locally stable, meaning if you started near them, you would get attracted to them. And that's what allowed the hysteresis effect to be seen for those who did that. All right, so this is, you could have this case. If you want an example, this is the kind of thing that would happen in a mechanical system where you've included damping, or where damping is included. So that was one possible scenario. So here's like scenario 1. Here's a second scenario. Let me sketch the real and imaginary axes on a complex plane. Plot the unit circle. There's a unit circle. And for this case, I still have an eigenvalue 1. So I only have 2 other eigenvalues, and maybe one is here on the unit circle, and it has to have a complex conjugate. So So the other two eigenvals are also on, on the unit circle. So what does this mean? This would mean, in terms of a Poincaré section, here is that point, and the other two eigenvalues being on the unit circle would mean that if I have a perturbation away, that here's the 0th, you know, here's maybe the first piercing after that, here's the second, here's the third, fourth, fifth, and so on. What I'll get is some points, they're not growing away from the periodic orbit or the fixed point of this map. They're not getting any closer. This would be the case of this is neutrally stable periodic orbit. It's neutrally stable and surrounded by quasi-periodic tori. Right? If I chose some other initial condition on here, I'd get some other closed curve. So this would be something you might get in a Hamiltonian system with no damping. I said a couple possible scenarios. I guess I should say a few, because I'm going to give you another. So here's another scenario. Complex plane of the eigenvalues of the M matrix, my unit circle is there. I've got an eigenvalue 1, of course, but then I've got an eigenvalue, whoops, I don't know what happened there. I've got an eigenvalue inside the unit circle. It's real. But then, oh, I have an eigenvalue outside the unit circle. Okay, what does this correspond to? Well, if you get the eigenvalues corresponding to these two directions, this one and this one over here, it's going to give you, in fact, maybe I will color that one in orange. It corresponds to stable and unstable directions. So you've got a confused periodic orbit. So here's the periodic orbit, or the fixed point. And there is, well, I'll show you what happens to some initial condition. I have an initial condition up here, let's say. And then, ooh, it's getting closer. It's getting kind of closer. And oh, what is it doing? It's moving away. It's moving away. How can this happen? It's because corresponding to this eigenvalue, we have an eigenvector that is stable. So we got a stable direction. Meaning if you start on that, you would asymptotically approach, but you'll probably be a little bit off. And if you're a little bit off, just like here, then there's also going to be a unstable direction. And the unstable direction is what will dominate in the long term. Except for a set of measure 0 of initial conditions that are on the stable direction. In general, most trajectories will look like this thing, and it looks like they are on like a hyperbola. So everywhere there's hyperbole, and things, points are, I'm drawing what look like continuous curves, but of course points are jumping along. But it looks like the typical picture of a saddle point. It's a discrete version of a saddle point. So how would we describe this? I mean, technically, this is an unstable periodic orbit, at least of these three scenarios. It's definitely the least stable. So for this case, we have an unstable periodic orbit. I would call it a saddle type, just to remind myself that, well, there is a stable direction. So, and this is the type of situation you would also get in a Hamiltonian system with no damping. In fact, you could even have damping and still have this. You get saddle points. It's kind of interesting to try to plot what this looks like out in the phase space, like in this picture in the upper left. What would it look like to have these stable and unstable directions? And I don't draw that very well, but other people have. And so I'm going to show that picture. It's kind of nice. Okay, yes, this one. So this gives an idea. This is from, I think, Wiggins' chapter on Poincaré maps. So here they've written this as the periodic orbit. This is what we call the x bar of t. Here's an initial condition along the periodic orbit, and then we've got stable and unstable manifolds along that Poincaré section. But of course, if you extend it out, where are these directions going? It's kind of like this extruded X going all the way around. So if I were to start with some initial condition, maybe I'll make it blue. Blue here on the stable manifold of the periodic orbit, it's actually crawling along, and it's going to get closer and closer to the periodic orbit. Of course, if I'm on the unstable direction, unstable manifold, then this is something that will be moving further away. I can draw or insert another picture of that. Just another. Oops. So this is just another picture of the same thing, where we've got the periodic orbit, we've got this Poincaré section here, and what happens to initial conditions. If I had an initial condition that was exactly along the stable manifold, then it kind of goes around, it'll come back and be closer along the stable manifold, having the distance shrinking exactly according to what the Floquet multiplier says. I've got a video that kind of shows this. It's worth showing, if it'll work. Yeah. So here's a periodic orbit, minding its own business. This is just kind of showing locally the stable direction and kind of what the flow looks like along it. It's worth stopping and looking at. Right? We just kind of grew it out. You can kind of see these arrows. I'm sorry that it's a low resolution. And now we're also showing the unstable direction, and these arrows are moving away. And of course, we've got both of these going on. And if we were to do a cutaway, there's the cutaway of what's going on in the periodic orbit, near the periodic orbit. Maybe I should show that video again. Is there something near the end that's intriguing? We're showing just the local parts of the manifolds. So this is like the local stable and unstable manifolds. But what if we followed these out farther? Let's say we took some initial conditions along them and just followed what the trajectories did. Then we would get this much larger. I mean, that's going really quick. Maybe we should slow it down. So here's a cutaway, and then we're just sort of showing if we extended these things out further, they might actually intersect and wrap back and do interesting stuff in the full phase space. So this is the idea of taking those local manifolds and then globalizing them. And usually this is done numerically. And there's a whole cottage industry on how to do that correctly. But then you get these nice, pretty pictures. I don't know if I can show it here. I think these are just higher resolution, higher quality, the same sort of thing. Stable, unstable, both of them together. This is looking at just the stable manifold, and on the left, we're sort of showing a slice through it, and then the unstable manifold and a slice through it. And in the movie, we saw how the two enmesh. And this is, if that situation happens where you have the stable and unstable manifolds intersecting one another, that's what leads to chaos. So if I took I've got my kind of local picture, the Poincaré section, like I drew before. I'm not sure how I drew it. I'm probably gonna have to orient it differently just to match what I've already got in my notes. So orange is the unstable, green's is stable. And if I were to, this is just the local picture, right? The local picture of the dynamics. And this is just a small slice of something that could be very big. What's the bigger picture? The bigger picture could be, and this is for now just a schematic, but you saw this kind of behavior when you did that computation for homework problem 1. Right, you can see that coming from an unstable point, a saddle type periodic orbit, which becomes a saddle type fixed point of the Poincaré map, you've got these unstable manifolds. So here's this unstable manifold, and it might do some interesting things. You might wonder, why is it doing all this curling? Kind of has to, it has to do it, and hopefully we can get to that. And so then you get this kind of thing. What is this green thing? The green thing is the stable manifold. And they can intersect. What happens at the points where they intersect? Well, we will get to that, hopefully. The intersection points are heteroclinic trajectories. So this is very similar to what you saw in numerically in that homework 5.1, right? Except instead of one fixed point, you had 2 fixed points, and they're stable and unstable manifolds. And you definitely saw this sort of curling and wrapping up behavior. And it's a consequence of the geometry. And maybe we'll be able to get to that during the last lecture. But right now, I wanted to talk about if we specialize to the case of Hamiltonian systems. So far, what we've been talking about is general for anything that's of the form x dot equals f of x. But now we will specialize to f of x is of the form that comes from a canonical Hamiltonian system. So suppose our equations of motion f of x are from a Hamiltonian system. And here I mean the canonical Hamiltonian system with no damping, so no non-conservative forces. That means that f of x, well, first of all, x is in an even dimensional space, and f equals that canonical symplectic matrix times the gradient of a Hamiltonian function. So J is, I guess we could write it that way. Right. N is even. So capital N equals n minus 2 is the number of degrees of freedom. All right. In this case, the monodromy matrix for periodic orbit is a symplectic matrix. And if you remember what that means, it means M transpose J times M ends up equaling J. And because of this, the consequence of this is that we pick up another, the matrix M, we already know it has one eigenvalue 1. Well, because of this property being a Hamiltonian, coming from a Hamiltonian system, being a symplectic matrix, we get another eigenvalue M. And I will physically try to explain where that comes from. Another eigenvalue 1. So that means the eigenspectrum is, in general, we have little n. So we've got 1, then we've got another 1, then we've got lambda 3 all the way to the end, lambda n. So now stability is determined by just these last n minus 2. And what is the physical interpretation for the eigendirections corresponding to these other eigenvalues? Well, the first one, it's due to the same thing as before. This is for perturbations along the periodic orbit. The second one is more interesting. Oops. And maybe I'll call this direction E1. This one corresponds to perturbations to nearby periodic orbits on nearby energy surfaces. And let's just call that direction E2. So a picture to have in mind, and this is just a schematic, would be, we've got here's a periodic orbit. And let's say here's the point where we're at this point. Here is E1, because we're always evaluating at some particular like initial condition point. Here's X bar naught. This is all living on a particular energy surface. I don't know why it made that so dark. So this is, let's call this energy surface E1. So this is a n minus 1 dimensional energy surface. And I'm gonna have to, whoa, I don't like that. I'm gonna have to move this down because I got more I want to draw. There's also other nearby energy surfaces. Here's like E2. No, that's not a signal. It's an E. Let's say E2 is like E1 plus some small change in energy. It's another energy surface, and by continuity of equations, the equations of motion, there has to be another periodic orbit on that energy surface. So E2, that was E1, this is E2. E2 points to nearby energy surfaces. In fact, periodic orbits along that nearby energy surface. So if we were to kind of plot, there could be a family, a whole continuous family of periodic orbits. One periodic orbit on each energy surface.
So in a Hamiltonian system, it's impossible to have isolated periodic orbits?
Yes, in a Hamiltonian system with no non-conservative forces, so kind of the traditional conservative Hamiltonian system, that's right. There are no isolated periodic orbits because you could always perturb to a nearby energy surface and find one.
So does that mean that in order to write a, you might say that a necessary condition to be able to write a Hamiltonian system in terms of, canonically and with a Hamiltonian, or to write a system, is that your periodic orbits cannot be isolated. So if you have a system that has an isolated periodic orbit, it cannot be written as a canonical Hamiltonian system.
Correct. I mean, it might be a canonical Hamiltonian with just some little dissipation.
Right.
If you add dissipation or damping, this picture gets altered, but it's an active research area as to how it gets altered. So we don't really know, but yeah, technically correct. If you've got a system with an isolated periodic orbit, it cannot be written, the equations of motion cannot be written in this way, right? It's not J times gradient of a Hamiltonian.
Okay.
So let me just label what this kind of blue dash thing represents. This is a continuous family of periodic orbits. If we want to be really fancy, say they are foliated by energy. Now it could be, right, these periodic orbits, they might kind of shrink down to a point. So there might be an energy below which there's no periodic orbit at all. And then there's a bifurcation. In fact, in this case, it'll be called I think it's a Hamiltonian Hopf bifurcation, which gives rise to periodic orbits.
Now, this does not guarantee that there will be for every energy a periodic orbit. It only guarantees that every periodic orbit within a certain energy neighbor will have a periodic orbit nearby it.
Yes.
Okay.
Yeah, it's all just written in the neighborhood form.
Okay.
Yeah. All right, so that's one thing we get. That's the interpretation of the second number one in the eigenspectrum. Now, what about these n-2 eigenvalues? Well, because M is a symplectic matrix, if lambda is an eigenvalue of M from a Hamiltonian system, then so is 1 over lambda. That's what we get from this being, from M being a symplectic matrix. We already knew, since M is real, that if lambda is an eigenvalue of M, then so is lambda conjugate. But now we get this extra thing that, well, so is 1 over lambda conjugate. So let me just show some scenarios quickly of at least what the eigenspectrum looks like. So for capital N equals 3 degrees of freedom, so this means little n is 6. We're talking about a 6-dimensional space. What can we have? We can have, so this is the Floquet multiplier eigenspectrum. Let me show the unit circle. We're going to have two eigenvalues that are here at 1, and we know how to interpret them. If we have something that's outside the unit circle, so let's call this lambda. Well, because this is a real matrix, M is a real matrix, we get lambda bar, but we also get 1 over lambda. And we'll get 1 over lambda bar. So it's like they come in groups of 4. This is called a, if we had a periodic orbit that had this as its spectrum, this is called a complex saddle type periodic orbit. And it arises from a quartet of eigenvalues. That's one scenario. So maybe I'll say here's, you know, a couple, and I will leave it as just a couple scenarios. Here's one. It's another scenario. Let me stick with the 3 degrees of freedom situation and then just plot another eigenspectrum. With my unit circle. Got 2 eigenvalues, 1. So now I've got 4 left to play with. If I have one that's along the real axis and it's outside the unit circle, so I'll call that lambda 1, then I've got to have something that's along the real axis inside the unit circle with a value of 1 over lambda 1. These will correspond to the 2 parts of the saddle. Lambda 1 is the unstable, and 1 over lambda is the stable. So then I've got, if I can have lambda 2 and then lambda 2 conjugate. And 1 over lambda 2 doesn't pick up anything new. It just picks up the same thing. This would be called a center saddle type periodic orbit. For those of you studying orbital mechanics, these are called, the most famous orbits that do this are called halo orbits in the 3-body problem. The 3D 3-body problem. Halo orbits have been used for missions. They're these kind of 3D orbits that look like the edge of a potato chip, and they have a stable direction, an unstable direction, and then they have these 2 saddle directions. So a two-dimensional center direction means directions in which perturbations neither grow nor shrink. And those correspond to tori around the halo orbit. The tori around the halo orbit are sometimes called quasi-halos.
The other center, oh, sorry.
Yeah, go ahead.
The other center direction is just the Lyapunov orbit direction, right? The one that leads to the ones on nearby energy surfaces. So there's the
so it would lead to nearby halo orbits on nearby energy surfaces.
Okay. Oh, okay.
Yeah. And yeah, if you want to know more about that, there's a whole book. ShaneRoss.com/books. All right, I'm going to introduce in the time that we have left, because it's kind of fun. I don't know about your kind of fun, Dr. Ross. Chaos in Hamiltonian systems, with and without damping, because it's a nice thing to end on. So I guess you could consider this an intro. You've already gotten, you didn't know it, but you've been getting an intro the whole time. Chaos and Hamiltonian systems. And this is with and without damping. And we'll look at the case of a time periodic system because it's the easiest to describe. Although there is chaos in time independent systems, like the three-body problem. It's just a bit harder to describe. So I'll look at a time periodic system, the Duffing system. So remember the ball moving on a track that's shaken at a particular frequency with a particular amplitude and with damping present. I'll just sort of state this up front, that chaos is often due to saddle type unstable periodic orbits. So like, what do we mean by that? Basically, they're stable and unstable manifolds. Intersect and have consequences. Like in that movie I showed. So the example that we'll look at is kind of our new pendulum. Instead of the pendulum, we're talking about the Duffing system. This is the Duffing system with unstable middle point. It's sometimes called the, maybe I haven't used this, the double weld, because it's got two stable welds on either side of that unstable point in the middle. So this is the same thing from last time. I'll just write the first order ODEs, x dot equals y dot equals x minus x cubed minus delta y. So, you know, you do whatever scalings, non-dimensionalizations are necessary to get things into this form. And then this is the form. I guess last time we had introduced, you call this thing theta, and then theta dot equals omega. So this looks like a system that comes from a Hamiltonian, but with damping and forcing added, where the Hamiltonian function looks like 1/2 y squared. Y plays the role of momentum, so this is like a kinetic energy term. And then we've got a potential energy, it's 1/2 minus 1/2 x squared plus 1/4 x to the 4th. So that's our potential energy plus damping and forcing. If we look at the situation with no damping or forcing, then we've just got the Hamiltonian system, and we could look at what the phase portrait looks like. Here's x, here's y. The phase portrait with no damping, no forcing, we can get an idea of what it looks like by looking at isocontours of this Hamiltonian function, viewing this Hamiltonian function as a height function, and then just looking at level sets, right? So there'll be, there's, this has two sides. We'll just focus on, we'll just look at the right side, well region. So there's an equilibrium point, and energies near that equilibrium point. It's a local minimum of the Hamiltonian energy. And so we have things like that. There's the origin is an unstable point. So coming out of it is we want, you know, there's a unstable and a stable direction, but I'll just plot it black because they meet up. The stable is the unstable. The snake swallows its own tail. And then you've got some other things going on outside of that. This particular curve that's made up of the stable and unstable manifold of this point, I don't know what to call this point. Maybe I'll call it P0. P0 is the saddle fixed point at the origin. This is for delta and epsilon equals 0. No forcing, no damping. This curve made up of the combination of the stable and unstable manifolds. I will call it capital gamma P0. And it is the stable intersected with the unstable, because they're actually the same thing, so it's just the same curve. That's also called the separatrix. Right, because it separates things that are inside, which would be stably oscillating around this in this right side well. I'm just not showing the left side well. That's all I mean by that. And it's separating that from things that are outside that are actually going around both wells. So the separatrix, it separates qualitatively different behavior. What we will talk about next time is we'll look at this. We'll embed this in the extended phase space to look at the time element, and then turn on damping and turn on forcing and see what happens. And what we will find out is that when damping's not 0 and when forcing's not 0, this separatrix, instead of meeting back up, it breaks. In fact, that's what they call it. The separatrix breaks, the breaking of the separatrix. And then you get a picture much like I showed up here, and which you saw numerically with the last homework. This is the breaking of the separatrix, but it's nice to see it, starting from the simplest case where there's no forcing, no damping, and then, what are the details of how it breaks and how is that related to chaos? So that's what we'll end with next time with the final lecture.